I'm happy that you joined to this webcast here, an introduction to JavaScript fuzzing. Before we dive into the talk, let me first introduce myself. So my name is Norbert Schneider. I'm a senior software engineer here at Code Intelligence, and I'm one of the people responsible for our fuzzers. That includes our open source fuzzers like Jazzer, our fuzzer for the JVM, and Jazzer.js, our recently released fuzzer for JavaScript, and also our internal fuzzers and integrating all of those into our SaaS platform. So Code Intelligence offers a platform that allows you to easily fuzz your own applications without any hassle. So if that sounds interesting after this talk, please reach out to us. Yeah, what are we going to talk about today? So first I will introduce fuzzing, a little bit history, the components involved, how everything works together, and then we will switch to JavaScript fuzzing, how that works, and finish everything with a few live demos. I imagine that quite a few are not familiar with fuzzing. Even in the, especially in the JavaScript ecosystem, I'm not aware of much use of fuzzing. So you probably wonder what's all the fuzz about. So at the basic level, fuzzing is kind of a testing technique that allows you to discover bugs and security vulnerabilities. And here on this slide, I put a few numbers of famous projects or applications, so like Office, Linux, Chrome, and all of those use fuzzing to discover bugs. And the numbers are not up to date anymore, probably, but you get the rough estimation, and you see that fuzzing is used in the industry to discover real problems, real bugs. Also, vulnerabilities were found by fuzzing. Everything kind of kicked off with the heartbeat vulnerability that was, that broke the internet a few years back. And there's a really nice introduction on how you can discover heartbeat while you with fuzzing. So that's really easy. Also, the shell shock vulnerabilities were discovered by fuzzing. So you see, it really is already used in the field. From a history perspective, fuzzing is around for quite a long time. It all started with random testing back in the 50s, but the term fuzzing was coined around 88 by the University of Wisconsin. And as you see here in the timeline, the last few years it really kind of took off. So Google announced ClusterFuzz, their fuzzing platform. Microsoft announced their own fuzzing platform. And Google also offers an open source version where you can fuzz your open source software on the Google infrastructure. So you see it, got really prominent in the last few years, and many of the major players are involved here. But what is fuzzing actually? So the word fuzzing means to make or become blurred. In our case, it relates to the tests. So we're actually not really sure about which test input or what kind of test the fuzzer is used. So it's kind of blurry on the developer side here to discover bugs or to use while testing. And it does so in a really simple way. So on the most fundamental level, it looks like this. So the fuzzer generates input and uses that input to invoke a system under test. And then it tries to observe unwanted behavior from that system. And in the easiest way, that's a crash. The interesting part is now that the fuzzer not only tries to create one input, but it tries to generate as much input as possible. And it can do so in different ways. So, for example, it could use a structured approach where some kind of specification is used to generate input, or in a more mutation-based approach where input is evolved like in genetic algorithms. And the system under test in this scenario is, like you see here, a black box. So the fuzzer doesn't really know anything about the system. It can only observe some kind of effects outside. And as you can imagine, the inputs here could be quite inefficient. So the system under test could validate input on an initial level, an initial layer, and discard many of those right to begin with. So the system evolved to more of a gray box approach. Here, the system under test is observable for the fuzzer, or it provides some kind of feedback, some feedback behavior information back to the fuzzer. So the fuzzer can use that feedback to generate more meaningful and efficient inputs. There are different approaches to what kind of feedback the system provides. Currently, coverage-based fuzzing is really prominent. In this, the system sends coverage information to the fuzzer, so which code path were executed during one test run. And the fuzzer can detect if a different input caused other code paths to be executed in the system, and continues with those and discards other inputs that won't reach this level of code. Also, the system under test can provide additional feedback mechanisms like comparisons, for example. So whenever parts of the input are compared inside the system under test to something else, the fuzzer gets notified about that and can try to mutate this part of the input so that it would satisfy the test and also reach deeper into the system. The idea here is that if the fuzzer can maximize the coverage, it will also maximize the amount of bugs or vulnerabilities it would find. The system under test provides the feedback, as I mentioned, and there are also different approaches to that. So it could be implemented in a complete compiler, in a compilation step, another one, or in more dynamic environments, the system or the application can be instrumented, so changed, amended right at runtime. So there's no need for other code modifications. This leads us to this comparison here. So as I mentioned before, more the original idea is the black box fuzzing. Here the fuzzer doesn't know anything about the system, and it could potentially miss bugs or miss vulnerabilities in the tests and is inefficient. And the more evolved approach on the right, coverage-based fuzzing, where the fuzzer tries to maximize the amount of covered code and so detects more problems with the application. Fuzzing, as you probably imagine from the history, was originated in the C and C++ world. And so many people still think that fuzzing is only relevant for unsafe languages like C and C++. And while it's true that memory corruption is a critical issue, there are other categories, even for memory safe languages, that are still important and should be tested. I created two categories here. So the first one is functional bugs. This leads from uncaught exceptions, so really easy case here, to assertions, but also out of memory exceptions, infinite loops, other kind of timeouts, more general. Or you could also use fuzzing for kind of property-based testing, so that your application also always holds true to some invariants. So on the other side, there are security bugs. For this, you can create specific instrumentations that would detect these kinds of security bugs. We already used this approach in Jazzer, the JVM fuzzer, quite successfully. There we can detect a whole bunch of security problems like remote code executions, past reversals, different injections, and yeah, it's quite easy to extend, even with user-provided detectors here. So you see, even in memory safe languages, there is a whole bunch of problems that can be found with fuzzing. That leads us to Jazzer.js. We recently released Jazzer.js publicly, and it's a coverage-guided in-process fuzzer for JavaScript and NodeJS. It's based on libfuzzer, one of the prominent and stable open source fuzzers for C and C++. And it integrates libfuzzer for its fuzzing algorithms and bridges the gap between the C and C++ code or world and the JavaScript application world. And by doing so, Jazzer.js already provides quite extensive fuzzing capabilities. So it can reach deeply into the application that is tested and is able to detect the functional bug category I mentioned earlier on the slide before. And also interesting is that it's completely open source. You can visit the GitHub page, have a look at the code, and can, participate like in other open source projects. We're always happy to see contributions, so please visit the page and reach out to us. Before we start with the live demos, we first have to take a look at the components that are used in Jazzer.js to provide fuzzing in the JavaScript world. And in Jazzer.js, we provide a CLI. With that, you can start the fuzzer. So here it's called fuzzing library, and that loads a fuzzer plugin. It's a Node.js native add-on, so it's written in C and can interact with libfuzzer. And libfuzzer, or the plugin, registers an interceptor. So whenever code is loaded, we intercept that code and amend it with the mentioned feedback mechanisms. So the coverage mechanisms and comparisons and so on. Yeah, the fuzzer needs an entry point to start fuzzing. That is generally called a fuzz target. In this case, it's more or less a test function you know from other testing libraries that gets the fuzzer input as a parameter and can use that parameter or that data to generate everything it needs to call the actual code under test. And the code under test is then instrumented and can give feedback to the fuzzer to mutate the used input and so on and so on. If the fuzzer detects a problem. So like I mentioned, exceptions, out of memory, other crashes. Then a crash input is generated. That's basically a file on the file system that can be used to reproduce the problem that was found. And during fuzzing, the fuzzer saves interesting input, so input that changed the code coverage, and saves it into a directory that is called corpus here. So when you start your fuzzing run again, the fuzzer doesn't have to start at the beginning, but it can pick up the already discovered inputs and continue from there. So that's a huge performance win. Okay, so I think that should be it. With that, we can move to the live demos. You should be well prepared, hopefully, to get through the live demos with me. So I'm switching to my IDE here. For the live demos, I prepared a little JavaScript project. It's a normal NPM project, really small here, that we are not distracted by too much code. But basically, it's some kind of a server application that provides a few functions, process requests, synchronous, asynchronously, and so on. And we want to test those functions. And as you see here, like I mentioned, it's a normal NPM project. So we have this empty package.json file. Good, and now we want to fuzz the server functions here. To do that, we first have to add Jazzer.js as a dependency to our project. And we can do that like any other dependency. So down here at the console, I can make that a little bit bigger. We first have to make sure that we have the correct version. For that, we use NVM. And the important part is here, NPM version 8 is required. Okay, now we can use NPM to install Jazzer.js. We only need it as a dev dependency, so no need to include it in the production code. And we import Jazzer.js core. And this will download all required dependencies. Okay, as you see here, everything's finished, and yeah, it also shows up here as a dev dependency. By including this dev dependency, you also get access to the CLI, the Jazzer command. You can run that by using npx. And with -h, you get here, let me make it a little bit bigger. You get a nice help text that explains the command, all the parameters and flags, and even a few examples down here. So if you want to dig into the CLI, you can do that with this help command here. Good. So everything is prepared now to write our first fuzz test. To do that, we create a new file, here, a JavaScript file, and let's call it just fuzz target.js. Nope. Okay, so every fuzz target has to export a function called fuzz. Let's do that. Export module, this one, and the function is called fuzz, and it takes one parameter. Let's call that fuzz data. So this parameter represents a buffer that is filled with the fuzzing input of the current run. Okay, now we want to invoke the actual method we want to test. So we can require that. Server and server.js here. And now we call, let's start with the asynchronous case. Okay, and that needs request data. In our case, the most convenient way here is just to pass in the whole fuzz data as a string to this request function and see what happens there. So we don't have to split it up in different parameters for this case. And yeah, it's asynchronous like many JavaScript functions. So we have to await its finish and mark the function as async here. Okay, so our first target is now set up and we can start it down at the console here. So npx Jazzer, like before. And now we have to specify the fuzz target as a second parameter, or yeah, first parameter actually. And that's it, let that run. So here is the some fuzzer output. You see like the amounts of features that are discovered and the amount of execute per second that are executed here. And shortly it should find a bug. I think my system is a little bit stressed here with live streaming. But already found two things here that are compared, and yeah, finally. Here we see that it found a bug, an uncalled exception in this asynchronous function, and the error was triggered. So this is the actual error text here. Error triggered by request awesome fuzzing. So the fuzzer came up with the input awesome fuzzing, and that caused something in the server code to throw an exception that wasn't cached. Here you have also stack traces and so on, and the problematic input in different formats here. So now the fuzzer found a test, a failing input, a crashing input, and produced a crash file here for reproduction. We can do that by, again, using the Jazzer command, fuzz target. So we want to execute the fuzz target, but only on our crashing input. And doing that, you see it directly triggers this bug, and it just, well, executes our target with this one input. So it's really easy to reproduce errors once they are discovered. So up until now, we used the npx command, but you probably want to include Jazzer deeper in your Node project. To do so, you can create a script for that. Let's call that Fuzz, and it's Jazzer fuzz target. And with this, it's possible to execute Jazzer via npm. So npm run fuzz. As you see here now, also the fuzzer is triggered, and it's like any other npm dependency, as I mentioned. So you can just integrate it into your normal NPM workflow and your normal project setup and CI and everything you like. So that's one of the design aspects that it integrates seamlessly into the platform. Also, integrating Jazzer.js via a script tag allows us to run the Fuzz tests directly from within the IDE, so in this case IntelliJ here, and also to create breakpoints and to debug findings, for example. So when I debug this script here, then the application starts up, and you can see here we are now in the Fuzz target and can step through and observe our program. So that's really quite convenient. Okay, so let me just remove that again. Good. Okay. As you saw here, we tested the asynchronous function. And yeah, this is kind of redundant. So first we get a promise and wait that that is finished and return another promise. So we can simply return the promise directly. And here's the terminal. And let Jazzer.js directly wait for that. So we don't have to wait for the internal, the promise inside, but whenever Jazzer.js detects that the Fuzz target returns a promise, it will await the completion before it calls the Fuzz target again. And here also the exception was triggered again. This can be also used if you don't return a promise, but like in this case, only a string. That's also possible. So returning normal objects or primitive objects is directly supported here. And let's wait for the completion. It should be there any second now. Okay, ready. Yeah, so even returning objects directly works. And in JavaScript or in Node.js, the fuzzer has to take care to not block the event loop so that asynchronous execution is still supported. But like in this case, where you really know that it's a synchronous target, you really just want to test this synchronous function, you can actually block the event loop to get a speed up. So for that, we have this sync flag here, and that is, again, only supported for synchronous functions. When we execute that now, you see that it's faster. So here, like 200,000 invocations per second. And up here, it's, not so much. So there's a huge performance benefit of using this synchronous approach. But again, if you want to fuzz asynchronous functions, then you need the event loop and you need all the handling and synchronization between the different threads. But yeah, as a performance optimization, it's really quite handy to know that that exists. Good. Then let's switch to another function here. So the dangerous function, oh, that wasn't right, dangerous. And let's start fuzzing now. And no, I think it's already there. So this function gets stuck. So it's on a problematic input, it executes an infinite loop. So the fuzzer can't get any progress. And there's a timeout, a default timeout in the fuzzer, but we can speed it up a little bit by providing a timeout flag here. And when we now execute the fuzzer, it first has to trigger the bug. So a little bit of fuzzing is required. And as you see here, something took too long, took longer as 1 second. And we detected the timeout, or which could be used for a denial of service attack, for example. The timeouts are also dumped into timeout files. Again, the awesome fuzzing input here, and the file can be used to reproduce this process-intensive function. Another problem I mentioned earlier can be detected with this. Here we don't need a timeout, but let's see if it can be detected. Right, so this function, when the awesome fuzzing input is received, creates a memory leak, or in this case it's not a leak, but it's an out-of-memory exception. So a different kind of error that could be used for like a denial of service attack that could crash your application. So as you see, writing or using Jazzer.js to fuzz your application is quite easy. All you have to do is add the dependency and write your fuzz tests or your fuzz targets. And then it can detect quite a lot of problems in your applications. Okay, so those are the demos I wanted to show you. Let's switch back to the presentation. And yeah, that's basically it. I only have to thank you for participation, and hopefully you find it interesting and will try out Jazzer yourself, Jazzer.js yourself. Thank you.